Hi there, crew, and welcome to another episode of the Geology 101 video series, Physical Geology. I'm Geology Professor Shawn Willsey. Thanks for joining me. Today in episode 9, we're going to start looking at rock types. We spent the last few episodes looking at the interior of the Earth, plate tectonics, minerals, which are the basic building blocks of rocks, and now we're going to launch into our first rock type or rock group, and that's the igneous rocks. And we'll do a part 1 here and probably a part 2 and a 3 if needed as a follow-up to this. So welcome aboard. This is a geology series for those who've taken geology classes years ago and want a refresher, or for someone who's never had any formal coursework in geology but wants to learn. So wherever you fit on the spectrum, thanks for joining me. This is a series just for you. And while this course is modeled after my college courses, it doesn't have a lab component or a field trip component, but you can supplement a lot of that information with the other videos I have here in the series, particularly the Rocks and Minerals with Willsey series, and then of course other field trips that are relevant to whatever topic you're studying. So let's go ahead and get right into it here as we start our survey over the next several episodes looking at different rock types. It's important to start with the rock cycle. So the rock cycle is a nice graphical way of looking at how rocks change from one type to another and the processes that govern those changes. So we're going to focus this episode and the next one on the system that's kind of in the bottom and to the lower right of this diagram. So what happens to magma when it crystallizes either below ground or at the surface. Later, we'll get into concepts of what happens to rocks at the surface that are exposed, processes like weathering, erosion. Once we create sediments, those sediments can be then deposited, buried, and those can become sedimentary rocks. At any points in the game, notice there's some little shortcuts through the rock cycle. You can have rocks that are heated or pressure is exerted on them and they change into metamorphic rocks. But once we have rocks melted, we're back to this igneous part of the rock cycle. So this is just a little bit of a diagram that's helpful to understand how rocks change, generally slowly, on planet Earth over time. So we're going to be focusing on the igneous rocks. So igneous rocks make up a lot of the really fantastic and amazing landscapes we see on planet Earth, volcanoes and lava flows, which people get excited about. It might be a more passive eruption, it might be more explosive eruption, even some of the big scenery like at Half Dome in Yosemite. These rocks are the result of the cooling and crystallization of magma, and that can either take place at depth or at the surface. Notice I've used two words there that are somewhat synonymous in many people's minds, magma and lava. There's actually a little bit of a difference there. Magma refers to molten rock at depth below the Earth's surface, and lava refers to the same material once it's at Earth's surface. But there's also some important distinctions beyond that. Magma contains a lot of dissolved gases, which can sometimes affect how the magma cools and crystallizes, or what it does when it's in the subsurface. Once that same batch of molten rock makes its way to the surface, and we call it lava, those gases tend to escape or try to escape. They're actually expanding as they're getting closer to the surface with less pressure on them. And so there is a little bit of a distinction there. Magma has those gases dissolved in solution, whereas with the lava, those gases are expanding and coming out of solution. We'll get more into that as we focus on volcanoes here in a few episodes. So let's look at just how Earth generates magmas. What are some of the processes whereby magma is generated or created in the Earth? And a lot of these diagrams have a nice little graph that goes along with them. So the first way you can get magma, that you can create magma within the Earth, is probably the most simple one, the one that's the most intuitive, and that's just add heat. Basically take rocks that are solid, and if you can heat them up enough, you can get those rocks to melt, or at least partially melt, and we'll explain this concept of partial melting here in a bit as well. So if we have a batch of magma that's already formed, we might be able to heat up and melt, or at least partially melt, some of the rocks above it to generate even more magma. So notice over here on our graph where we have temperature and depth, if we hold the depth constant but we just move to the right in this case and increase the temperature, eventually we cross this little curve here which represents solid versus liquid phase, right? So over here the rocks are solid, but once we get past this line here and melting is in place, then the rock is becoming more liquid-like. It's becoming a different material. So this is one way that planet Earth creates igneous rocks and magmas is by adding heat, but there's another way we can do this by adding heat, and that's by over thickening the crust, which is commonly associated with mountain building. So in this case here, if you look at the bottom left diagram, in this case we have maybe a subduction zone or a thrust fault, something that's stacking rocks on top of themselves, and in doing so we've created a very thickened section of crust. The mountains are big, the crust is much thicker than it was previously, and so this same batch of rock that was maybe over here close to the surface or some depth below the surface, as this mountain building process takes place, notice now it's much deeper, and we know that as we go deeper into the earth, into the crust, the rocks get hotter, and at some point you can reach those critical temperatures whereby rocks become molten, or they at least start to melt a little bit. And the graph here shows the same sort of thing. In this case we're taking this rock and moving it to a deeper region. Well, deeper regions also correspond to higher temperatures, and so we've crossed this line here from the solid phase into the liquid phase. So this is one way that we get magmas generated, and you might think about places where we see igneous rocks of either erupting at the surface or maybe forming underground. So a good example of this first one here might be hotspots like in Hawaii or Yellowstone, where we have hot rock, maybe even magma coming up from depth, and that's heating the rocks above it, causing even more magma to be generated. Over here we actually have this process playing out in the Himalayas, where India is colliding with Asia. The rocks are being shoved over the top of other rocks, and so that creates a very substantially thickened pile of crust, which causes magmas to form, and those magmas can then cool and crystallize. Let's look at the second process now. This is called decompression melting. Basically, if we take a batch of rock and bring it up towards the surface, you can sometimes get that rock to melt because you're taking the temperature off of that rock. Or excuse me, taking the pressure off of that rock. So the rock is coming closer to the surface, there's less pressure above it, and that process in and of itself, depending on the rock types and some of the compositional things, may cause that rock to melt. It's not true for all rocks, but in certain circumstances this will take place. And a good example of where we might see this would be a place like Iceland, a divergent boundary, or the Mid-Atlantic Ridge, or underneath the Red Sea, where we actually have divergent boundaries that are pulling the two plates apart, and right at that plate boundary we have less crust or pressure pushing down on that lower section of the crust, or the asthenosphere, and so that generates melting there. So in this case we're holding the temperature constant and just moving vertically, and we've crossed that line into the melting region. So this is another way we can get rocks to melt, or again partially melt, is just by decreasing the pressure that's exerted on those rocks. And then finally, our last recipe for generating magma is one that's kind of counterintuitive, but it's an important one, and that is by adding water. Turns out water, and this is called flux melting, the water added to the rocks, specifically in the upper mantle, causes the melting temperature to be lowered. So it's easier to melt the rocks if you add water. So where we typically see this is at a subduction zone where one plate's diving beneath the other. This oceanic plate has a lot of water trapped in its rocks. These rocks were sitting along the ocean floor, and as those get dragged down into the overlying plate's asthenosphere or upper mantle, the water is actually driven off and causes some of this material to melt. Back when I took 101, I made the false assumption that it was the downgoing plate that was melting, and that's actually not true. So don't get duped into thinking that. That's an incorrect concept. It's actually the melt is generated in the overriding plate, in this case this continental plate, and it does so because of this water that's driven off. So it's kind of a catalyst or a flux. It actually changes the melting temperature of the rocks and causes magma to become created. Okay, so now we know a couple ways in which Earth generates magma. Let's actually take a look at magma itself and see if we can understand a little bit more about magma here. So we think of magma as just a liquid, but it's actually composed of solids, liquids, and gases. So all three phases of matter exist when we look at magma. Now the solid portion of the magma are the crystallized elements, the actual crystals that form. Sometimes those crystals are big enough to see when we eventually see them in rocks with the naked eye. A lot of times they're actually very small and we need some form of magnification to see them. The liquid portion is what we call the melt sometimes. This is actually what you really truly think of as magma, the melt. But it does have little bits of solids in there moving around in it. And the melt is just the elements that are unordered, the mobile liquid portion of the melt. If these elements can combine with other elements, then we start seeing, and they become solid, that's when we start seeing crystals forming. And then the gases, or what we sometimes call the volatiles, are the dissolved, these are usually dissolved in magma. They can come out of being dissolved, or out of solution, if you will, as it gets closer to the surface at a volcano. And these are just some of the types of gases that are often found within magmas: carbon dioxide, water vapor, sulfur, chlorine, fluorine. There's a host of others. There's sulfur dioxide, hydrogen sulfide, all sorts of different gases that exist in magma. And then what's fun is we can actually see in some rocks, we can actually see, which of course is a crystallized piece of magma or lava, but we can see all three of these phases here. So we can see these gas bubbles, right? So we can see where the volatiles or the gases used to exist when this was still molten. We can actually see these preformed crystals, in this case, these very beautiful green olivine crystals. So these already had formed within the magma. And then all the black, very fine-grained material here is what was once the melt. This was the liquid portion of the magma before it, in this case, erupted and then cooled. So that's what magma is made out of. Let's look a little bit at how magma actually crystallizes. So it turns out there's a nice, ordered, predictable manner in which minerals crystallize based on their melting temperatures. Not all minerals melt at the same temperature, therefore they don't all crystallize at the same temperature. And this has been verified and studied by looking at, taking a rock, putting it in a high temperature furnace, melting it back into liquid, and then studying the ordered manner in which minerals crystallize out of that melt. So this has been verified with countless experiments. And what we see is that as the minerals form, the composition of the melt changes, because every time you make a crystal, you're extracting out of the melt some elements that you need to make that crystal. And so the composition constantly changes. So let me show you, if that's a little bit confusing, let me switch over to the little desk cam here and see if I can explain this a little bit better with a diagram. So let's go ahead and go with this. I'll kind of be out of view here, so I'll just kind of shrink myself way down. And so in this case, what I've drawn for you is just a hypothetical volcano. Here's the big magma chamber beneath the volcano. And in this magma chamber, of course, if we assume it's at very high temperature and everything is in the liquid phase right now, we haven't made any crystals just yet. And so what we would have is just unordered elements, right? Just sort of chaos in here. And what are some of the typical elements we see in a magma? Well, silica, which is silicon, and oxygen are the two most abundant ones. So they're going to be in here in abundance, probably way more than I've shown here. This is just kind of a little silly and graphical, but let's just go with it. So there's silicon, there's oxygen, aluminum, some potassium, iron, magnesium, sodium, calcium. I think I touched on most of them there. So here it is, just an unordered, chaotic soup, if you will, of different elements. But as we start lowering the temperature, so let's take the temperature and start to drop it, which will cause these minerals these elements are going to find other elements that they bond with easily and start forming crystals. Now the first crystal that's going to form from this is a crystal and a mineral called olivine, those pretty glassy green minerals I showed you in that last rock photo. And what's the recipe to make olivine? Well, you need magnesium, you need iron, you need silicon, and you need oxygen. And olivine is quite happy and stable at these high temperatures. So that's why it's going to be first. It's going to be the first mineral to crystallize. So when I'm making olivine crystals, what I'm going to need to do is I'm going to need to take out of this magma soup here, these unordered chaotic elements, I'm going to need to take out some of the magnesium and some of the iron and the silicon and the oxygen. And every time I take those out, I make a crystal. In this case, a pretty green crystal of olivine. So I can keep doing that, take out some of the iron, the magnesium, the silicon, and the oxygen, and make myself some nice pretty olivine crystals. So what happens over time is as I keep making crystals, what I'm doing is I'm extracting and removing from the melt, from this magma system, I'm taking out the iron and the magnesium. Now you'd say, well, aren't you taking out all the silicon and oxygen too? Well, there's just so much of that. Let's assume that's in an abundant supply. But over time, the melt, what's left behind, the stuff in between the crystals, is going to be depleted in magnesium and iron. Okay, so let's get this down to some temperature. And now let's say we start forming something else. Now let's start forming amphibole crystals, which I'll show in blue. And to get those to form, we're going to need some magnesium, some iron, and some silicon and oxygen. So here's our recipe over here for amphibole crystals. So same sort of thing. To make one of these, I need to, oh boy, I ran out of magnesium. Let's add one real quick. So there's a magnesium, there's an iron, I need an aluminum, a silicon, and an oxygen. And every time I take one of those out of the equation, I can get one of these blue crystals to form. So let's do one more. Pretend there's a little bit more magnesium in here, and there's an iron. Got to take an aluminum. I need a silicon and an oxygen. So what you can see then is we're starting to form these different crystals, different minerals, but over time the chemistry or the composition of the remaining melt starts to change. Eventually we get to other minerals that don't even need some of those first ingredients. So we might get to muscovite, which needs some of the potassium, the aluminum, the silicon, and the oxygen. And so then we can start making fun little muscovite mica crystals. So I think you get the idea here. So what happens then is the magma composition changes as crystals start to form. Now you might say to yourself, well, now we've got happy green, blue, and red crystals all together. Turns out it doesn't work that way, because as the temperature keeps dropping, these olivine crystals, which were stable at high temperatures, might not be so stable as we get down to these lower temperatures, like where muscovite starts to crystallize. So these might break down and become some other mineral. And so we won't get too deep in the weeds with that there, but hopefully that's a little bit helpful there about how you get incremental crystallization in an ordered way in a magma system. So okay, so let's go back to the slides here. And if your brain's still working well, great. Nice thing about these videos, of course, is you can pause, take your time with them, whatever the case may be. Okay, so last couple of concepts here, folks. So it turns out by looking at the minerals that crystallize in magma and studying the order in which they form, there's a thing called Bowen's reaction series. And so what we see here is high temperature magmas at the top and then low temperature magmas at the bottom. We'll get to these words on the right here in a little bit, so don't worry about these words. What you'll see on the inside of this diagram, of course, is some of the minerals that we're a little bit more familiar with. And if you watch my mineral series, we've actually gone over all of these. So olivine, pyroxene, or sometimes it's called augite, amphibole, which is sometimes also called hornblende, biotite, potassium feldspar, plagioclase feldspar, muscovite, and quartz. And again, without getting too deep in the weeds, what this shows us is it shows us the relative temperatures and compositions, which we'll get to in a minute, at which these minerals form. So olivine is a high temperature mineral. It's going to form first. It's going to be associated with very high temperature magmas. Quartz, on the opposite end of the spectrum, is a very low temperature mineral. It's going to form at very low temperatures. And you'll never see these two, in a purely magma setting like this, coming out of the same batch of magma. You'll never see these two in the same rock because they're at opposite ends of this spectrum, and you can't have these two high and low temperature minerals in the same rock. They just it's not compatible. And so this is it's a reaction series, because what happens is the olivine, while it's cooling and crystallizing and the temperature is getting lower, it's reacting with the melt around it, and it can change that mineral into something else. Now you can get two minerals together. So olivine and pyroxene are buddies. They're quite happy together, but you're not going to see olivine with muscovite per se. unless something really crazy's gone on with, hydrothermal fluid. There's ways to do it, but if it's just a simple magma system that's cooling in a simple uniform way without any sort of other magmas involved or any sort of mischievous geologic behavior, then those two won't be together. So and then over here, again, we'll get to these terms in just a second. We have some rock types and we have some magma or rock compositions. That's where these words like mafic and felsic come into play. Okay, so this is Bowen's reaction series. So, last thing here. It turns out that you can reverse this process as well. So you can take a magma and crystallize it and cool it so the temperature is dropping till you get down to this portion. Or you can take the whole system and run it in the opposite direction. So you can take a rock and start to heat it up and see what melts first. And it turns out that these bottom minerals at the bottom of Bowen's reaction series, which are low temperature minerals, although they were the last to crystallize, if you heat up a rock, if a rock is being heated by some external or other heat source, those are the first minerals that will melt. So quartz will melt at a much lower temperature than something like olivine or biotite. So that's kind of handy as well as we look at sort of these crystals and their history, because they tend to sometimes get recycled over time. Okay, so a couple of things about magma types. So one term that will be helpful as we study both igneous rocks, magma behavior, and eventually volcanoes is this concept of viscosity. Basically, think of viscosity as the opposite of fluidity. So water, for example, which is highly fluid, is actually a low viscosity material. It does not resist flow well. It actually flows quite easily and readily. But if you take something like honey, for example, that actually has a fairly high viscosity. It's slow, it's sluggish, it's not very fluid, it doesn't move very quickly. And if you know anything about honey, you also know that its viscosity can change a little bit depending on its temperature. And so most of us know that if honey is, if you go camping and you reach for the honey for breakfast and it's kind of a cold, chilly morning, that honey will very much resist flow. It might actually almost be solid as you try to, get it out of the jar or the container. And of course, most of us know that you can heat that honey up and that allows it to flow more readily. And magmas work largely the same way. So remember this word viscosity. High viscosity, slow, sluggish, pasty, thick. Low viscosity, runny, fluid, and those are some good word associations there. So magmas come in various types, and we have classified these based on mainly how much silica they contain. This is important because magma compositions vary, therefore we get lots of different igneous rocks, and because magma compositions vary, we have lots of different types of volcanoes. So this fundamentally what dictates the volcanic behavior of any given location. So you might ask, well, why is Mount St. Helens sometimes explosive, and then when we get eruptions in Hawaii, they tend to be pretty passive in terms of, how dangerous they are? It's fundamentally tied to the magma composition. So if we have a magma that has a high amount of silica, let's say more than 70%, that will generally be lower in temperature. So again, think of the honey, right? When the honey's at low temperature, is it viscous? No, it's like thick and sticky and goopy and it doesn't flow very well. And the same is true with felsic magma systems. They have high viscosity. They don't flow well. They're not going to send runny lavas to the surface. They're going to tend to be very pasty. They're going to tend to trap gases, and these, as we'll see later, will become more explosive types of eruptions. Let's go to the opposite end of the spectrum here. So the opposite end of the spectrum is mafic magmas, which are appreciably lower in silica content. They tend to be a lot higher in temperature, so they're going to have some of those high temperature minerals like olivine that we talked about. They're going to tend to be much lower in viscosity. So when these erupt or make their way to the surface, these types of lavas are going to be very runny. The gases can escape pretty easily, and for the most part, these are going to be less hazardous and less dangerous. So if given the chance to live next to a volcano that was either mafic or felsic in composition, I guess I'd take the mafic because it's probably less explosive, although you could argue that the felsic volcano is maybe not going to erupt during your lifetime because it takes a while for it to erupt. But we'll get to all that as we get to volcanoes. And then, of course, there's things that are in between, right? So what if you've got, something in between, then it's an intermediate magma. Realize these are just artificial constructs. This is humans' way of classifying behaviors and things in nature. So and you can, of course, have anything in between along this spectrum. But in general, mafic magmas, again, lower silica content, higher temperature, lower viscosity. Felsic magmas, higher silica, low temperature, and high viscosity. Looks kind of confusing right now. I'd encourage you to write this down and kind of make those simple word associations to kind of cement it in your brain, because this is very important, very fundamental to how we're going to classify and study igneous rocks, and then also look at volcanoes and volcanic behavior as we move forward. Okay, so partial melting. We're almost done here, team. A couple things and a little quiz for you at the end. So we've talked about how things crystallize, but let's look at things going the other way. So here's a magma chamber, and of course we've talked about how those olivine crystals, those high temperature minerals, might form first. So here's our early formed olivine crystals, and because those are more dense than the magma that they're in, those might tend to settle down to the bottom. So that's going to make our composition of the magma at the bottom of the magma chamber more mafic. And because the felsic materials tend to be much more buoyant and lighter, that's going to concentrate more felsic magmas at the top. This is fundamentally, it's not a perfect example and it's very cartoonish, but this is fundamentally what's happening beneath Yellowstone. There is a mafic magma body at depth, and then above that there's a felsic magma body. They're not necessarily connected per se like we see here, but it's the same sort of thing. So notice what we've done here is just changed or zoned our magma chamber. So the other example I have for you here that's probably the better one, the one I like a little bit better, and it's a nice job here graphically. So notice if we start on the left here, we have a rock made out of, let's say, these dark, these green, and these yellow minerals. Okay, and let's say that the yellow minerals are felsic. So they're at the bottom of Bowen's reaction series. They're a low temperature mineral. Excuse me. And what we're going to do is we're going to increase the temperature on the rock. Maybe the rock's getting buried deeper. Maybe there's a magma body nearby. Something's causing this rock to heat up. Well, what happens to these minerals as the rock heats up? Well, the felsic minerals, as we just learned about, are going to be the first ones to melt, right? At the bottom of Bowen's reaction series. These are the first ones that are actually going to start to melt. And so we maybe melt completely, not everything, but just these felsic minerals. So notice they're turning orange here. And what we've done now is we've separated out that felsic composition from this original material. So now this is depleted in all the felsic minerals like quartz that was in it, and now we have a batch of melted rock at this temperature that was made out of these felsic minerals that so this is partial melting. We have taken the rock and heated it up. We haven't melted the whole thing, or we'd be back to just regular magma, but we've partially melted the felsic, the easiest stuff that would be allowed to melt. In this case, the felsic or the high silica minerals. Okay, so we've separated those out, and this is exactly what happens in many instances, is we can get separation of the original material by increasing the temperature and allowing these low temperature minerals to melt, and then they become buoyant and then they separate out a little bit. So okay, hopefully that makes sense. Again, this stuff takes some digesting, so if you're not getting it right off the bat, that's okay. You can watch again, you could deep dive on the internet and find some other resources, whatever works. So here's your quiz question, and then we'll wrap this up. So we've looked at Bowen's reaction series, and here it is again. So here's a list of 5 minerals. Okay, which of these 5 minerals would be the first, or among the first, to crystallize from a magma that had an intermediate composition? So you've got Bowen's reaction series there. You got the minerals shown here in the middle of the diagram. And if we had an intermediate magma, which one of these minerals would we expect to see crystallized in that magma type? So you might want to pause the video if you need a little bit more time. Maybe phone a friend, chat with a neighbor, look it up. In these environments here, you can cheat. It's not punitive. And then we'll go ahead and reveal the answer here in a second. So if you look at Bowen's reaction series here, let's see what we can, let's go process of elimination. What can we take off the table here? Well, sulfur's not even on Bowen's reaction series, so let's take that right out of there. So C's gone. We have an intermediate magma, so we have a composition that sits here in terms of temperature and silica content. Well, olivine is a high temperature mineral that we see in ultramafic and mafic rocks, so we can take that out. Quartz is dominantly in felsic or low temperature magmas, so we can take that out. Muscovite, same thing, dominantly in felsic or low temperature magmas. It's a good buddy with quartz, so we'll take that out. But amphibole, which you see right here shown by this arrow, is a mineral that we see a little bit in mafic rocks, but we see it dominantly in intermediate rocks. Occasionally it's maybe an accessory mineral in a felsic rock, but it really, if you see quite a bit of amphibole in a rock, you most likely have an intermediate composition in your magma. So that would be the correct answer there, D. And then finally this graphic here from a textbook many years ago, I can't remember which one, nicely kind of shows the same sort of thing. And what you can use this little chart for is if you can identify just one mineral in your rock, like if you are convinced and positive your rock contains quartz, let's say, then what you can do is kind of just, you can see where quartz sits here on this spectrum of magma compositions going across the top here. And you can see who quartz's buddies are. So what other minerals might you see in that rock if quartz is already there? Well, you might see some potassium feldspar, usually kind of pinkish. You might see plagioclase feldspar, which is going to be white and usually makes kind of square rectangular crystals. There could be a little bit of muscovite, a little bit of biotite, could be a little bit of amphibole, but what you're not going to see are these two minerals over here, olivine and pyroxene, because they do not exist at those same temperatures or compositions as quartz. And so this is a handy little table that might prove useful as well. So, alrighty, hopefully that was helpful. That's part 1 or episode 9, looking at igneous rocks. We will follow this up, of course, with a part 2, episode 10. We'll be looking specifically at our igneous rocks, and we will start defining and using some of these terms you see up here, like gabbro, diorite, andesite. If you've always wondered a little bit more about these rock names and types that you might have heard before, we'll do a deeper dive with those. So thank you for your support. Thank you for watching this episode of the Geology 101 series. Appreciate you, and we'll see you next time. Take care.